Great to see you here again. We are continuing our session of videos related to prime numbers. And in this video, I will look into conjectures and open problems that relate to primes. It will be a rather short video, but that's not a problem. There are some interesting things that we can find here. First of all, we look at the number theory and conjectures. Now, it is in fact known that number theory is a subject in which it is easy to formulate conjectures. Some of them can be proven, although very complicated, while others still remain open and no general proof has been found until now. An interesting conjecture was the polynomial n squared minus n plus 41. Which results in prime numbers for n smaller or equal than 40. And of course, since we have a limited number of calculations, it's easy to prove them. And we also would like to see what happens when n is larger than 40. Is it possible to extend this conjecture to larger numbers, larger than 40? Now, when we put 40 in the equation, we find that it is 41 to the square minus 41 plus 41. Which is basically 41 to the square. Now, is this a prime number? Well, no, it's not a prime number, it's a composed number, because we can write this number as 41 times 41. It's a product of two prime numbers, which means it's in fact a composed number. Like I said before, there may be a lot of conjectures, and lots of them have been proven, but many of them are still open. And we call them the open problems, which are still waiting for a proof. And some of them already have been accepted by mathematicians that they will be true, and they expect that a proof will be found soon. Now, when we have the conjectures proven for a large number of cases, we can of course use these cases, but we also have to be careful that we go outside of the scope, outside of the range that has been proven. It may be that the conjecture is not valid anymore. Anyway, any number that we add to the conjectures, we always have to verify, and we have to see if the number that we get is really a prime number or not. Now, when we look at the conjectures, one of them is a very well-known conjecture, which is Goldbach's conjecture. And we have also some effects or influence and elements relating to Euler. Now, Christian Goldbach conjectured in the 18th century that every odd integer n larger than 5 can be written as the sum of three primes. Now this means, for example, 7 is 2 plus 2 plus 3, 3 plus 5 plus 5 for 13, and so on. Now he shared his findings with Leonhard Euler, and Leonhard Euler said that this conjecture is basically equivalent to the conjecture that every even integer for n larger than 2 can be written as the sum of two primes. So we have 4 is 2 plus 2, 8 is 3 plus 5, and so on. Now, Goldbach's conjecture has not been proven formula. There is no general proof of this conjecture, but it has already been proven initially by hand calculations and later by computer calculations that it is valid for large numbers up to 4 times 10 to the power 18. So it's quite a large set of numbers that we can consider here. Now, typically, we have to be careful when we say that this is true or not. Mathematicians, however, based on the fact that so many examples have been proven already, they accept the truth of this conjecture, and they assume that a proof will be found in the near future. So people are working on finding the proof. Until now, at the information I have, it hasn't been proven yet. Anyway, people expect that it will be proven. So these conjectures can be quite interesting when we're looking at integers and at prime numbers. So that was about the conjecture about the sum of the primes, we also have a very interesting conjecture, which is the twin prime conjecture. Now, we look at many conjectures that exist, and there is, for example, one of them saying that n to the square plus 1 gives you a prime number, and we find that this conjecture was proven in 1973. So we say 17 is 4 to the square plus 1, 37 is 6 to the square plus 1, 101 is 10 to the square plus 1. Those are in fact prime numbers, and we can extend this as being a general formula because it has been proven. Now there is also what we call the twin prime conjecture, and it states that there are infinitely twin primes, and twin primes are prime numbers that differ by 2. So the simplest examples are 3 and 5, because 5 minus 3 is 2. But we find other twin primes less than 100, and they are 5 and 7, 11 and 13, 17 and 19, 29 and 31, 41 and 43, 49 and 61, 71 and 73. But we can find more twin primes like this. Of course, the calculations become more complex when we go to larger and larger numbers. The element is that this list is growing. People are finding more and more twin primes, which is quite interesting to know how we can use primes later in, for example, encryption. Now that was about the conjectures, some open problems, but very important to see that we can find conjectures, that we can prove them, that we can find relationships between numbers and prime numbers, but also good to know that there are problems that have not been proven yet, and those problems are part of what scientists are looking for, and for some of these open problems, very interesting prizes can be earned. Now, what we're going to do in the next session is to look at what we call the greatest common divider and the least common multiples. These are some elements that are very important to understand when we are dealing with encryption. So we're looking at the basis of these elements here. You're doing a great job. Keep on the word, keep on watching the videos. If you want to review something, there's no problem. You can go back to the previous videos and you can view them as many times as you want. Anyway, have fun, learn a lot, and I'm looking forward to seeing you in our next video. Thank you and bye-bye.